All right, everybody. So time for u-substitution part 3. And to take stock of where we have been, all right, where we're going, I told you that in the first video, the goal for u-substitution is to take a problem that has like a complexity beyond where our basic rule applies, okay? So like maybe I want to do this problem, but I have this rule. And just the stuff I see there's too much stuff. There's more stuff here. I mean, it might sort of look like this rule could apply to it, but there's too much stuff. It's not simple enough, okay? So the idea with u-substitution is to substitute the variables so that the basic rule becomes applicable, okay? Now, we have other basic rules than the ones I've already talked about. So here are a few of our basic rules in addition to the one that I've discussed in the other video. So here's the type of problem and the rule that I've discussed so far. But there are these two also. The antiderivative of e to the x is e to the x plus c. Okay, why is that true? Well, this is an indefinite integral. It's also called an antiderivative. It just means that if you took the derivative of this, you get this. Okay, yes, the derivative of e to the x power plus some constant is e to the x power. Here's another one, all right? The antiderivative of 1 over x dx is natural log absolute value of x plus c. Quick word on what those numbers are. E is about 2.718. Has many applications. We can use it to calculate compound interest. Population growth models usually depend on E. Lots of things do. And natural log, ln, is a logarithm with a base number E. Okay, and so to fully understand that, you'd have to know a little bit about logarithms too. But so let's say for now, those are our basic rules. Okay, so here's a problem that ultimately we can work with substitution, but as it is too complicated for these basic rules to apply. So what we need to do is figure out a way to make a substitution like I showed you in other problems, okay? Like the goal with this first problem I showed you is to choose a substitution for u. You let u, this new variable, be some aspect of this problem. All right, and you substitute u and du into the problem, the variable and the differential, and then it becomes simple enough for our rule to become applicable. So same thing is going to be true here. How am I going to do that to get one of these rules to apply? Well, if I have 3 rules, okay, and then this one is only applicable if n is not -1, then this right here looks like of everything, it would most likely be this one, okay? So like I'm gonna think like this. I'm gonna say I think that this rule up here is the one that might work. Now, in order for that to happen, in order for this to be simplified enough so that that rule applies, my substitution would need for u to be this thing there under the bar. So let's do u is equal to 10 plus 8x. Okay, all right. So at least then it'll be like over u, kind of like this. Now I don't just substitute the u and the x, I substitute the dx also. So once this is chosen, I take the derivative of both sides. So the derivative of u is du for these purposes, and for 10 plus 8x, the derivative of that is 8 dx. Okay, all right. Now I want everything here to fit, and so this will be the u, right? And it looks like it's almost going to fit. Like this part will be u, but what about this part, like the dx? I got to substitute that away, and that has to be the du. And I've got this 8 here. Like the equation I'm working with is du is equal to 8 dx, and this doesn't say 8 dx. If anything, it says 3 dx. It doesn't say 8. but all I want to do is make this fit into that problem. So what I'll do is I'll treat this like any other equation, and I will divide both sides by 8 because then this thing will fit and I'll be able to substitute it. So I get du over 8 is equal to dx. All right, so now between this and this, I'll substitute, and this will be reduced down so that that rule is applicable. So let's do in this step right here. I'll substitute both of those. I'll get the antiderivative of 3 over u, and then dx will be du over 8. Okay, all right, now I've got some other numbers than I want. Like I want this to be 1 over u du. Then it would be like this rule, and I could use the rule and work it, I'd be done. What about the 3 and the 8? Well, that is just a number in there, which is 3/8, 3 over 8. And in indefinite integrals, you can factor out constants if you want to. So throughout my videos that I've made lots of rules, or I've made use of lots of rules, and I've told you of lots of rules. But there's a rule that says if you've got some constant k times your function times dx, if that's all multiplied together, then we can factor out that constant k, and then we could solve this indefinite integral with whatever the rule would be appropriate. So I got a 3 and an 8, I can factor that out, and then I get 1 over u du. Okay, so yeah, this is where I want it to be. Like at that point, this rule is applicable. Okay? So that's the goal of u-substitution, is to get to that point where that rule is going to work. Here we are. So let's see. I got 3/8, which I'm just carrying along. And according to this rule, the antiderivative of 1 over u du is natural log absolute value of u plus c. So 3/8 times that. My final answer, given that u is the very same thing as 10 plus 8x, is 3/8 natural log 10 plus 8x. Absolute value plus c. All right, and there we go. We got what we want at that point. Okay, so let's see a few variations on this where either one of these rules could become applicable. All right, so what about this one? So this one, like for sure, looks more complicated than our rules would allow for. I mean, I've got a rule for e to the x and a rule for 1 over x, and this has way too much stuff in it. 6x to the 5th power times e to the power 5x to the 6th. So that's not going to work the way it is, but I'm thinking if I make the substitution correctly, then I can use this rule. Of those rules that I showed you, okay, so here are basic rules that our substitution will take us to. This is the one that looks most like what we have, okay? So think about like this. How could you substitute some portion, some aspect of this? You're going to let u be something. Like you're going to choose some aspect of this, and you're going to let u be that. What aspect or portion of this could you make that choice to be so that this rule could become applicable? Seems that the power would be the thing that you want. So we'll say 5x to the 6th. Now the rest of it's got to fall into place too, because I substitute the x, all right, for u, but I got to substitute the dx for du. Like the x has to completely be substituted away. I've got to remove or eliminate the x entirely by substitution in terms of u. So to follow with the rest of that, I take the derivative of both sides of this to get the differentials involved. Okay, so I get du, the derivative of the left-hand side of that. And what's the derivative of 5x to the 6th power? So I bring the 6 down, and I get 30x to the fifth power dx. That kind of looked like it might work. Okay. I'm not worried about the 6 because I can factor out constants. But let me rewrite this a little bit to show you that I think we're almost there. Okay. Just going to rearrange things just a little bit like that. And like everything's still there, I just rearranged it. So you can see that this part will be u, and then I'll see if I can get this part to be du. I mean, I'm close. I don't see anywhere in this problem 30x to the 5th dx. I see x to the 5th dx. So like I'll try to use this so that I can substitute there. That's one way to do it. If you ask different people, they might tell you slightly different ways that you handle this part of the substitution. Bottom line is what I'm working with has to all go up there. So I'm going to divide both sides by 30. And then I'll get like so. Okay. And then it will fit. All right. So let's do this. With this and this. Okay. In there, here's how the substitution is going to look. I get this number 6. That's just a constant. I get e to the power u. That's what I was hoping for. I wanted this rule to become applicable. For x to the 5th dx, I get du over 30. Okay, so there. Now it's looking like it's coming together. Like it's almost like that rule now. Okay. Problem is I got this 6 and this 30, but that is like a 6 on top of a 30. So let's write like 6 over 30 like this. E to the u du. All right. Then we got it. It's like right there. Now I can use the rule. At that point, I can do it. Let's do that. Let's use the rule, but let's also adjust this number. Because, yeah, I did have a 6 over 30, but that would reduce to 1/5. Okay? All right, so 1/5. Then the antiderivative, according to this very simple rule of e to the u du, is e to the u power plus c. And then my final answer, putting in my original variable x, u is the same thing as 5x to the 6. I'll get 1/5 e to the power 5x to the 6th power plus c. All right, and then there we got it. Okay. Let's look at one that is a compromise between this first one that I did and this second one. What about this one? Okay, so here it has the e in it. It's got the exponential expression. It's got e to the power 8t. So you might think that it's kind of like this one. The problem is I see it in 2 different places. Okay, all right. If I had it in just one place, then I would think that it would be like this rule. But the fact that it's in 2 places seems to make it a little bit different. But let me tell you something else. I mentioned this in another video, the video I made right before this one. And there are a few different ways you can think about how you choose this, because when you use u-substitution, you have to choose this part, okay? So you can choose that part because you want the problem you have to reduce down to some basic rule. And so you choose it so that that happens, or so that it seems like it would happen. Another way that you can think about choosing this is you choose this part so that if you took the derivative of it, you would get something a lot like the other unchosen part of the problem. So it's like, look, if I let u be this, 5x to the 6th, the derivative of that is 30x to the 5th. You see this here? This is not 30x to the 5th. It's 6x, but it doesn't matter. Like the x to the 5th is the part that I can incorporate with the differential to substitute away. So I choose the u so that if I take the derivative of it, it will be the other unchosen part of the problem, perhaps with the constant factor being different. So if it's a 6 instead of a 30, no big deal, all right? Okay, so that's another way that you can think about it. And I think that's valuable here, because if I let u be this bottom part, like this, let's see, u equals 2 plus e to the 8t, notice how the derivative of that, the du, is the top part. What's the derivative of 2 plus 8t? Well, we happen to know our rules for derivatives in that case, but it is derivative of 2 is being a constant is 0, plus derivative of e to the 8t is 8 e to the 8t dt. And that's this top part. All right, okay. Now, if we had chosen the other way, that wouldn't have worked out, you see? But choosing it this way is such that everything fits. And that's ultimately the goal. So let's see. I'll do a little rewriting. I'm going to put a 1. I'm going to separate this fraction out. I'll say 1 over 2 plus e to the 8t power times 8e to the 8t power dt. Because that's the same thing. I separated it out. It's kind of, if you want an analogy to numbers, it's sort of like saying, suppose I had 2/3 times 5. Suppose I had that. That's the same as 2 times 1/3 times 5. Okay, same exact number, same exact answer. You can rearrange it like that. So here I do this because, look, because I chose it that way, this is the u and this is the du. And like I said, everything fits. I have to completely substitute away the variable t and get it completely in terms of u. All right, so let's see then, if I do that, then this is in fact u. U is 2 plus 8t. That was my choice. 1 over u. 8 e to the 8t dt. That's du. Okay, and there we go. Now, do we have, is this some basic rule? Remember, I said, like, no matter how you choose to do it, your basic rules have to become applicable. Like, is one of these now applicable? I mean, do you have x to some power n, as long as that power is not -1? Do you have e to the x power? Do you have 1 over x? We have this last one. We have 1 over u du. Okay, so our basic rule is now applicable at this point. All right, so right here, we're going to use the rule. This substitution took that complicated looking problem and reduced it down to this one, simple enough for our rule to apply to it. That's the goal all the time. All right, now, so we choose our substitution in a way that if we took the derivative of that, what we choose as substitution, it would be the other unchosen part, except possibly with the constant being different. Here the constant's the same and we don't have to worry about that. All right, so what's our rule say about the antiderivative of 1 over u du? It says natural log absolute value of u plus c, like that. Okay, and then so in our case, this will be natural log, and then u is 2 plus e to the 8t, so we'll say 2 plus e to the 8t plus c. Okay. All right, now let's look at an application. In this application I'm about to show you deals a little bit with that plus c. All right, now I've talked about that plus c a lot. It's called the constant of integration. It's there because if you took the derivative of natural log of 2 plus e to the 8t, you would get this original expression if you use the rules. But if you took the derivative of that plus any constant, you would still get this. So that's why the antiderivative has this plus c all the time. You go back to the first video I made about the indefinite integral to know a little bit more about that. But let's look at this problem, and I'll tell you how the constant of integration comes into it. So let's say that we have the marginal cost function for some product. So here's our marginal cost function, and it gives the marginal cost in thousands. So if this told me 6, that would mean 6,000. Okay. The x in this expression, in this marginal cost function, is the number of units of the product, whatever the product is, that are produced. So we got the marginal cost in thousands, we got the number of units that are produced. Okay. Question, could you find the cost function given that there is a fixed cost of $15,000? So first of all, the marginal cost is the derivative of the cost function. Okay, so it's like I want the cost function, but I have its derivative. Remember how I just told you that this is the antiderivative of that expression that's given? So yeah, that's the tool I want to figure out the answer this time. Okay. But it says find the cost function. I have the derivative. All right. Another thing, the marginal cost tells you, very rough description, the cost of producing an additional unit from any point that you want. So if you put in, say you let X be 100 units are produced, and you put that in here, whatever this told you would be the cost of producing the next unit. So no matter where you are in the production phase, no matter how many units you've produced, the cost of producing that next unit may vary. It may go up and down. It may not be constant. And that's what the marginal cost tells you in rough terms. Okay, so let's see. I think we have enough information to solve this though. So let's do first step. Let's do like this. If you want the cost function and you have the marginal cost, its derivative, then the cost function would be the antiderivative or indefinite integral of the marginal cost. Okay, so it's going to be the antiderivative of 72x over 6x squared plus e. E is just a constant. Remember, e is about 2.718. Now, in order to evaluate this indefinite integral, I'll need to do u-substitution. And that will involve reducing this down to one of the basic rules. Okay, like this one, or this one. And this is the one I think it's going to be. 1 over x dx. Antiderivative of that is natural log absolute value of x plus c. I think it's going to be this last one. Let me show you why I think that. So let's do like this. To solve this, we're going to use u-substitution. I'll let u be this bottom part. 6x squared plus e. That will be my u. And I think this will be 1 over u du once I get the substitution all worked out. The du, okay, because remember I substitute the variable and the differential. So I choose this substitution, I take the derivative of both sides, and then I substitute the differential. So du on the left, what's the derivative of 6x squared plus e? That will be 12x dx. Why 12x dx? Well, the derivative of 6x squared is 12x. You bring the 2 down, 6 times 2 is 12x. And then e is a constant. E is about 2.7. The derivative of a constant is 0. Okay. Now, it looks like this will work for us. Let me do a little rearranging. Okay, I'm going to write 1 over 6x squared plus e. I'm going to take this 72x and write like this. So this is times, and then the dx. So does it look like everything is going to fit? Like, so there's u, okay? And then I got 72x dx. And I need to make that fit there. It's like, I got 72. And I got, here's 12x. And 12 and 72, they're not the same. I need to make this fit. Now, I could do this lots of different ways. I can divide both sides by 12 and substitute for x dx if I wanted to. But I can manipulate this equation any way I want so that it fits up there. So another way that I could do this is, let's see, if I want this to fit up there, and this says 12x dx, but up here it says 72x dx, could you multiply 12 by something to get 72? Yeah, I can multiply it by 6. I'll take this equation, I'll multiply both sides by 6. You can do that. You can take an equation, you can multiply both sides by whatever you want. And I'll get 6 du on the left, and 6 times 12 is 72x dx. Here, the bottom line is we just need the substitutions to fit. I have to substitute the u somewhere up there by my choice, and then I have to substitute the du somewhere up there too. And now I can get it. All right, so let's do this, these two substitutions right here in this step. Whoops. It's going to look like this, 1 over u, and then 72x dx is going to be 6 du. So this is 1 over u times 6 times du. What about the 6? The 6 is just a constant. I can factor it out. When we solve antiderivatives or indefinite integrals, we factor out constants is fine. I do like that. And now my rule applies. Like right here is when I've gotten something that is too complicated for one of my basic rules to apply. And now I've got it so that it works. Okay, so now we're going to use the rule. So what rule? Well, there was that rule up there at the beginning of the video where he said antiderivative 1 over x dx is natural log absolute value of x plus c. So let's see about that. I'll get 6 natural log absolute value of u plus c, because u is my variable at this stage, okay? And then u is 6x squared plus e. So 6 natural log absolute value 6x squared plus e, and then plus c. Okay, so there we go. I've got it, a partial answer. Okay, now my question was to find the cost function. So let's write down this way. Let's say partial answer. This definitely isn't the final answer. Okay, but we could say the cost function is 6 natural log absolute value 6x squared plus e plus capital C. Now, the issue at this point is that this might be the cost function, but this constant here that shows up every time we find an antiderivative or evaluate an indefinite integral is there, and we don't yet know what it is. And so to fully know the cost function, we'd have to know what that number was supposed to be. So let's use the additional information. Here it says that there is a fixed cost of $15,000. Okay, so think about what that means, like fixed cost. So you might think if you were producing something, there would be a cost to produce every unit, but then there would be some costs that have nothing to do with how many units you produce. So like say, I'll have like simplify an example. Say you're making something and you've got to have a factory. Okay, so you've got to lease the factory or something like that. Then you pay that cost whether you produce anything or not. Now, once you have the factory and the machinery and all that, you secure the raw materials and energy to produce what you're producing. And those costs depend, at least in part, on how many units you produce, because you're using up raw materials and energy, okay? So the fixed cost, it's like, this part's like saying if x is equal to 0, you haven't produced any units, then c of x is 15, okay? Not 15,000, because I was given that the marginal cost function was in thousands, so the cost will also be in thousands. So 15 means 15,000. So that's like an extra bit of information I can use to find that constant. So let's go take care of that in our second step. So our second step is, it is known, or it was given, that c of 0 is 15. Okay? So I'm going to take my cost function, I'm going to put 0 in it, and I'm going to say that what I should get is 15, and I'll find that constant of integration. Okay? So I'll get 6 natural log absolute value 6 times 0 squared plus e, okay, plus our unknown constant c is equal to 15. All right, then I'll solve for c. So let's see, 6 natural log 0 squared is 0, times 6 is 0, plus e is e. So I get 6 natural log e plus c is 15. Now, from here, you could use a scientific calculator if you want to, or if you really understand logarithms, you won't need a calculator for this one, but natural log of e is 1. So this says 6 plus c is equal to 15. If I subtract 6 from both sides, I'll get c is equal to 9. All right, I found it. There's my function. Now that this number is known, I know that function. I could use it to do calculations. I could put in my production and calculate the cost. If I didn't know that number c, that extra constant, I wouldn't be able to do that because I wouldn't have enough information. I have a number that was missing. Okay, so let's do this. Let's write our final answer up here. Your cost function is 6 natural log, absolute value, 6x squared plus e, and then plus 9, because we found that constant is supposed to be 9, right? It is supposed to be 9. You could also lose the absolute value if you want to, because 6x squared plus e will never be negative, so it's not like there's a point to having the absolute value. The absolute value is included in the formula because it might be that that variable could be negative sometimes, but here x is the number of units you produce. That's positive. You square it, it's positive. You multiply times 6, it's all positive. So I'm going to put either one of these as acceptable, just in case. You know my math lab is a computer, and who knows, it might be expecting some certain format and not understand an equivalent answer, but that would also be okay if you omitted the absolute value. All right, but there it is. There's our cost function, and that's what we're looking for in this one.